Welcome back, everybody. And off we go. Do we have any ideas for our next segment? I may have asked before people had started to rejoin the Zoom.
Okay. I was looking at the SN1 versus SN2, like I
Yes,
guess the vocabulary, the polar product versus a product. So I was thinking maybe just do from the fall 20 part 2 with
sure.
where going through the steps to determine a couple of those maybe.
Absolutely. Let's get that fired up over here. I think the best way to go is here. I'm looking for fall 20 test 4. There it is. And should take a second here. Can I bring that over? Looks like it. A little fuzzy there, but we can make that. Part 2. Oh, went right by, didn't I? Yeah, you're talking about these guys. These are all chapter 9s, and you're going to have 4 of them. We can do at least the first 2 and see where we got from there.
Sure.
We'll take one at a time. Yeah, let's grab the title too. Here we go. All right. So we have to look at the carbon with the leaving group first. And halogens are excellent leaving groups. They're not the only leaving groups, but it's a good start. So let's do analysis of carbon with leaving group. I call RX. And this is our analysis here. There you go. Okay, leaving marks everywhere here. Okay. Primary, secondary, or tertiary. Let's see. A carbon that has just 2 bonds to carbon. And there's no alkenes around, so you're not even talking about allylic in this one. So just 1 carbon, 2 bonds to carbon, secondary. And that is the circumstance where we can't make an immediate conclusion. So you show that. And the reason for that is the activation energy to make a carbocation, SN1 involves carbocation, is the same as the activation energy to get through a backside attack. That's the SN2. So as you're studying, always keep in mind SN1, carbocation, SN2, backside attack. Just keep those words always flowing through your mind. Next, you analyze your nucleophile. Good short form for nucleophile is nu. And that's this species here, this anion, RO minus. And that R is just a good old ethyl group in this case. So there's no resonance involved to stabilize this anion. And anions are typically strong nucleophiles unless they're resonating. Strong nucleophile favors SN2. So far I'm leaning towards SN2. Don't skip any steps in the analysis. I need 3 steps for 3 points. If you go ahead and make a conclusion based on any of the earlier steps and stop your analysis, you're just throwing away points. Solvent, ROH. This ethanol is a solvent that can hydrogen bond. We call those polar protic. It's SN1. 1. And you're saying, wow, how can I make a conclusion now? I got something that says I don't know. I got something that says SN2, something says SN1. Oh, there's also something else. RO minus, this is an override, which means it actually takes over from all the analysis. There's an override. RO minus has a pKb of -3. You don't have to write that on the test. You could write strong base, and every time you have a strong base plus heat, the override gives you a big fat conclusion of, yes, conclusions. What color would be good for conclusions? I don't even know. I can't change my pen color. That gives a bimolecular elimination. That's what the 2 stands for, is bimolecular. E stands for elimination. So you also need a conclusion. I don't know if this is the fastest way to get to conclusion, but it's one way. And there we have it. So that's 4 points for everything we've done so far. And then we got 4 more points available for predicting our products. E1, E2, you've got to find all the beta hydrogens. What the heck did I just say there? Beta, what's that mean? Well, beta is the letter in the Greek alphabet after alpha. Alpha is the carbon with the leaving group. Beta is any carbon that moves 1 away from that. Not 2 away, just 1. Beta carbons have to have an H for elimination to happen. And yes, both of those beta carbons have H's. One of them is actually drawn for you, and the other is now drawn here. And major, since we're on the subject here, I was hoping I could move down my answer so I can just write my products underneath their titles up there. And I can. If you grab this H here, this beta H with the base. In fact, I'll do the mechanism for just that one. This is not a mechanism question. You don't have to give me any mechanisms. Grab H, sigma becomes pi, leaving group leaves. You eliminated H and Br. You have a pi bond in between them. So I'm going to draw what could be major or minor. Let's see how, after I draw it, how it looks. And we'll put it in baby blue. You're going to have a double bond from here to here. In the minor, oh, there's a methyl here. In the minor, has the ethyl cis to the isopropyl. That's a rather long ethyl, isn't it? There. What's the difference in these two products? They both have the same H missing. The H off the carbon with the methyl. Ah, yes, this one has the bulky group on the left of the alkene on the same side as the bulky group on the right. Isopropyl, ethyl. H is not bulky at all. This one has the bulky isopropyl on the opposite sides of the alkene. It's E to the bulky ethyl. That's why it's major. And this one's minor. Now to get 2 more products, we consider the other H. And that would give, I'm not going to show the mechanism for that one, but that would give this double bond here. Oh. Double bond there. And this stereocenter wouldn't change because you didn't grab that H. And you got that. And the minor version of the same thing, it's a methyl, it's an H, and we got this and that. Here, the I didn't draw that the greatest, but trying to fix it up. There we go. Yeah, it has the bulky groups on the same side. Here, the bulky group here, opposite of the other one. So why do we like these two products the best? They have 3 carbons attached to the alkene. I'll put dots on them. 1, 2, 3. 1. No, that's not attached to the alkene. 1, 2, 3. We call those tri-substituted. Tri-substituted has more hyperconjugation. Oh, wow, that hyperconjugation stuff's for a lot of things. That's these two. Tri-substituted, tri-substituted, then di-substituted. If it sounds vaguely like the same discussion for cation stability, it's because it is exactly the same discussion. It's the same concept. It's hyperconjugation. So these two have more hyperconjugation. So why is this one better than the minor here? Because it's got the same hyperconjugation and less steric hindrance. So there you have it. So that's good for that. Let's do at least one more in this segment. Let's get the second one. And we'll grab the, we'll grab it in 2 parts. Make this a little bigger. Snippy. I don't need the title anymore, do I? Just grab this. Number 2. And halogen seems to be missing this time. Don't be upset. All right. Our analysis. I don't know. They're supposed to be the same all the time. Analysis and conclusion. No, it's not going to let me do that. Don't know if it'll save any time. Can't hurt though. And looks like the secondary is going to be the same. Nucleophile is not RO minus. So we're going to have to change category, possible conclusion. And I don't think the override's going to be thing going on here. It won't let me erase the box. Oh, I stand corrected. Oh, life's harsh. Could have rewritten everything by now, right? I like the box. Move the box. Where's my eraser? There it is. Well, it is polar product, but it's not the same kind. All right. I'm going to do our analysis now. There you are. Okay, Rx is secondary. Why? Because this carbon has 2 carbons attached. It's not allylic. You can't add that word because this carbon isn't an alkene carbon. I know you see an alkene carbon. You're tempted to say allylic. Do not. This carbon would have to be allylic. First of all, this is the leaving group. Oh, we even have to draw the leaving group. Leaving group Lewis structure. As many of you have read already, excellent leaving groups are the conjugate bases of strong acids, and perchlorate fits the bill. Yes, and it does say Lewis structure. Oh, octet violation. Shame on teacher. Still got my chunky fat eraser going. Let's get rid of that lone pair. No octet violations allowed. Don't forget your formal charge. That thing is so resonance stabilized, it's very stable. Okay, there's your leaving group. It qualifies as an X. Secondary, we don't know. Nucleophile is an amine. It's not got a charge this time. It's neutral. HNET2. It's polar. No. We don't call that. That's not a category. I'm looking ahead of myself. I'm getting ahead of myself. It's a moderate. Do you want the three choices of nucleophile? They're easy to remember. Strong, moderate, poor. Does moderate sound like it's a real decision maker? Answer no. Tell me you know that. You still haven't made a decision. What do you do when the solvent appears to be missing? It's very common, by the way. It's not missing. There's always a solvent here. Well, when the solvent appears to be missing, the solvent is the nucleophile. The reaction's called solvolysis if you read about it. And yes, it's a hydrogen bonding solvent again. H bonded to N here. H bonded to O in the previous example. H bonded to O. Those are both hydrogen bonding solvents. What category are those? Polar product. What do they favor? SN1. I don't have any overrides here. I got something that says I don't know. Something says I don't know. And something I say that I do know. And that's the only one that is making my decision. Carbocation. Was that just random? That word just came up random? No. Whenever you say SN1, you should say carbocation to yourself. You're not going to get points for drawing the carbocation, but it will definitely help you think about the reaction. Because everything you learned about carbocations before is still relevant. And the new fact that if you can get this thing to be allylic, then you've added 1.5 degrees to its stability, which means it'll be higher than tertiary. And that ability to move an atom from a position 1 away from a carbocation, that better not be new for anybody. This is called a hydrogen shift. We saw it in chapter 6. It's not going to go away. And this new cation is exceptional. Tertiary allylic has roughly the same stability as a fictitious 4.5 degree cation. You add 1.5 degrees to the original number if you're allylic or benzylic. You want to see benzylic real fast? I'll erase it in 10 seconds. This would be the same conclusion. Why is it called benzylic? It's on a carbon, 1 away from a benzene. Has the same stability as allylic pretty much. Not part of this question, but you saw it. Tertiary allylic 4.5. Yeah, so I'm loving this cation. My major product better have the nucleophile attached to this position. And that's what I'm going to draw up here. Major nucleophile there. The nucleophile was H bonded to N. It's blue. With 2 ethyls. That gives this thing a positive charge when it has 4 bonds. Those are very stable. You already knew that from chapter 4. Got a stray mark here. What I mean by you saw that it was stable in chapter 4? What's the pKa of an ammonium ion? 10. Is that strong? No. It's weak. Weak means stable. It stays just like that. You do not take that proton off. Minor would be the SN1 reaction that came from the original cation. It's not as stable as the first one, so I don't expect as much product from it. I have no idea what just happened. Oh, I had my hand on the screen again. It's starting to happen about once a day. Don't forget, It's an ammonium ion. Okay, that's minor. Now you're out of products that are called SN1 products. You got to remember, for every SN1 reaction, there's also an E1 reaction that's minor. E1s are never major. And in elimination, you can do an elimination from this cation or this cation and pretend like it's E2. In your mind, have the leaving group still there. You grab the H from a position 1 away. And instead of it moving, it's just something grabs it. You want the mechanism? Why not? You asked for it. So instead of the nucleophile attacking, we'll do this one. 1 away from the cation. Nucleophile is the amine. Instead of being a nucleophile, sometimes it acts like a base. And it's going to give us the most minor product right there. I'll tell you why it's the most minor in a second. Minor 3. Not as stable as minor 2. Where's minor 2 come from? Well, you grab either this H here to make minor 2. It's got to be on a position 1 away, right? Or do it from the tertiary. Remove that H. I'm not a big fan of ever showing this on tests. I think it's the first time all semester you're going to see it. I don't like seeing it. I'd rather see the mechanism. Here, this is a minus H plus right here, and it shows how it happens. This is better than writing that. You're never going to get points for that. But this is not a mechanism question, is it? So we can, in our mind, I have to lose the H there, and I get these 2 minor products. These are E products, both of them. E1. Why E1? Because they came from carbocations. So if you have a 1 in the name, you better be having a carbocation in your brain. Okay, so we did the first 2. What I'll do is we'll stop here. Do you have anybody have questions before I stop here?
Nope.
All right, and I'll come back and we'll see if you want us to go on. All right.